Welcome to the third genetics video, 4.B.4. I can interpret a pedigree to determine the following inheritance patterns, phenotypes and genotypes of individuals in the pedigree, and the probability of future offspring having certain genotypes and phenotypes. If more than one individual in a family is afflicted with a disease, it is a clue that that disease may be inherited. A doctor needs to look at the family history to determine whether the disease is indeed inherited, and if it is, to establish the mode of inheritance. This information can then be used to predict the reoccurrence in future generations. A basic method for determining the pattern of inheritance of any trait, such as eye color, or even a more serious disease like Marfan syndrome, is to look at its occurrence in several individuals within a family, spanning as many generations as possible. For a disease trait, a doctor has to examine existing family members to determine who is affected and who is not. The same information may be difficult to obtain about more distant relatives and is often incomplete. Once the family history is determined, the doctor will draw up the information in a form of a special chart called a pedigree or family tree that uses a particular set of standardized symbols. For males, we will always use a square. So there's my square. For females, we'll always use a circle. If either one of these individuals is affected by a disease or has the trait is showing that phenotype, then we shade that shape in. If we are heterozygous or a carrier, then we are not showing the trait, but we still have one allele that would code for the trait. In those cases, we shade in half of the shape. Now, a carrier is still going to be heterozygous, even if it's X-linked or is on a sex chromosome. However, a female is the only person or the only individual, excuse my little markup there, but a female is the only person who can be a carrier for an X-linked gene, because if a male has an X chromosome, the Y chromosome probably doesn't have that gene, so it's unable to be a carrier. If it has the allele on its X chromosome, then it's going to show that phenotype. So a female can be a carrier, and if she is, then we just put a dot within that circle. If any individual is deceased, we just put a slash through their shape. When we have two individuals mate or get married, we connect them with a horizontal line. If they get divorced, then we put two slashes through that horizontal line. Consanguineous mating doesn't happen very often anymore. It didn't happen real often, but every once in a while you may see it. And in that case, we have two individuals from the same family tree mating. And so we'll show that with a double horizontal line. Now, we already showed that when two individuals mate, they have a horizontal line. For their offspring, we draw a vertical line connecting our mates and their children. So we'll give this family a girl and a boy. Now, if two parents are going to adopt a child, then that child is not a part of this bloodline. However, we will still show that child with a dotted vertical line. And then we will also bracket that individual with kind of a dotted bracket. If we are putting a child up for adoption, then they are a part of this bloodline, and so we connect them with a vertical line. But this time they're leaving the family, so we take a solid bracket and put that individual within the solid bracket. The last thing we want to go over is twins. Monozygotic means we have identical twins. Identical. And for identical twins, we're going to have our parents, and then the children come off at an angle. And so here are my twins, and if they're identical, then I'm going to connect these two angled lines with a horizontal. Dizygotic means non-identical, and so we're just going to get rid of that horizontal line. So there we go. Now, if we don't know whether it's dizygotic or monozygotic, then we'll put a question mark right here indicating that we don't know. So that's the basics of all the symbols that we use in pedigree charts. The next thing we need to look at is we've got these numbers. On the side, we have Roman numerals, and these Roman numerals indicate generation. So in this pedigree, we have 4 generations. And you could look at it as grandchildren, children, parents, and then grandparents. In each generation, we use Arabic numbers, numbers that we normally use, to indicate birth order. So who's born first, second, third, so on and so forth. And these numbers are important so that we can talk about and identify individuals without describing where they are on the pedigree chart. So let's take, for instance, this individual right here. Instead of saying it's the last male born in generation 2, we simply say that this individual is individual 2-4. And it's that simple. Alright, so now I've given you 3 different pedigree charts, the first being a dominant pedigree. Whenever we look at a pedigree and we're trying to determine whether it's showing a dominant trait or a recessive trait, we're going to start with the children and work our way backwards. And the reason for this is if we have an individual that's affected in a dominant pedigree, that means that at least one of its parents has to be affected as well. And that just makes sense. If we're going to have a dominant allele for this guy right here, then it had to have gotten its dominant allele from one of its parents. And if his parents had that dominant allele, this individual is obviously homozygous recessive, since we're talking about a dominant trait. But one of his parents had to have had the allele as well. So every individual that is affected has at least one affected parent. Also, if we have an affected parent like we do here with individual 2-1, and they're married to an unaffected parent 2-2, those 2 parents have a 50% chance to transmit this phenotype. And we see in their children, we have just that. We have one of their 2 children showing this phenotype. The third thing about dominant pedigrees is that if we have 2 affected individuals that get married and mate, they may have unaffected children. They don't have to. We could have 2 heterozygous if this person was heterozygous and this person was heterozygous, then there's a chance that a child might not be affected with this disease. Now with recessive pedigrees, we're going to work backwards again. And that's because if we have an individual and neither of his parents show that trait or show that phenotype, then it has to be a recessive pedigree. Now we can have a parent that has the phenotype or showing the phenotype, and one of their children could show the phenotype as well. But this is the key, this situation right here. If we have an affected child and his parents are not affected, then we definitely have a recessive pedigree. Also with the recessive pedigrees, if we have two affected parents, then they will definitely transmit that phenotype because both of these parents are homozygous recessive. And so the only alleles that they have to pass on are those recessive traits. Now finally, if we have recessive or if we have dominant pedigrees, something to keep in mind is that we do have Mendelian rules at work, but we don't always see them because of a small sample size. Each family, each set of parents are only going to have a few children. If each set of parents had, say, 20 or 25 children, then we might see more of those Mendelian ratios that we've been talking about for the last week or so. Finally, let's talk about X-linked recessive traits. So this is a pedigree chart of an X-linked trait. Well, how do I know? Well, I know because there are many more males than females that are showing the phenotype. In fact, we don't have any females that show the phenotype. We only have males. Now, we do have some females that are carriers, but we don't have any that are actually showing the trait. And that's going to be true of all X-linked recessive charts here. The other thing that we need to keep in mind is that if we have no offspring of an affected male are going to be affected, and we can see that right here. We've got an affected male and none of his offspring are affected. However, all of his daughters are going to be carriers, and that's because they are getting an X chromosome that has the disease or the allele for the disease. They're getting that X chromosome from him. The males that are his children, however, are getting the Y chromosome, so they're not getting that disease allele. Alright, so here are the pedigree questions that are on this Google form. Use this pedigree chart to answer questions 1 through 9 and make sure you submit that to me. Good luck with that, and we'll see you in class.